So we have found arithmetic sequences and then their sums. Now we've worked on identifying geometric sequences, and now we need to work on finding their sums. So we are going to find the sum of both a finite and an infinite geometric series. Now if you remember with arithmetic, if it was finite, you could add up numbers, get a sum. If it was infinite, you could not add up an infinite amount of numbers in an arithmetic sequence and get a finite answer, because you're just adding and adding and adding and adding, and your numbers are just getting bigger and bigger and bigger, so your sum is not approaching anything. In fact, we would say that that sum diverges. It goes to infinity, okay? But with a geometric series, you can find the sum of a finite, and you can add up an infinite number of numbers and get a number. What? Ms. Schwartz, you're crazy. No, it's true, and we're going to talk about that more throughout this video. So, just to remember, these are your formulas for finding geometric sequences, okay? We choose to use this x value, so you don't always have to have your initial condition. We're going to need those throughout today to work on finding these sums. So, I wish I had a fun Gauss story to tell you about who came up with the sum of a finite geometric sequence, but unfortunately I do not have such a story. This is the finite geometric sequence. So go ahead and put this formula in the box that's in your notes. And we're going to go ahead and label a few things. This is going to be your starting value. Just like with the arithmetic, this is the value of the first term being added, but it doesn't have to necessarily be the first term in the sequence. Okay? Remember, we can start, like on one of them we summed from 5 to 25. So it's the value of the first term being added. Doesn't necessarily mean that n has to be equal to 1. Okay? Then r is going to be your common ratio. And n, change colors here, is going to be the total number of terms added. Got n over here too. Okay, so if you were summing up the first 100 terms, this would be a sub 1, and then this number would be 100. All right, let's use it. Given the sequence 6, 18, 54, sum, that's what this sigma means, that sequence from 1 to 12. Well, in order to use our formula, we need to know a sub 1. A sub 1 for us is equal to 6. We need to know our r value, our common ratio. 18 divided by 6 is 3. 54 divided by 18 is 3. So our common ratio is 3. And we need to know how many numbers we are summing. Well, we're summing from 1 to 12, so n is going to be 12. Let's go ahead and find that sum. S, then, is going to be our initial value, 1 minus r to the n over 1 minus r. Go ahead and take out your calculators. If you type it in exactly as you see it, okay, you should get the right answer. And that correct answer is 1594320. I'm sorry, I don't have my calculator on my computer still. Alright, so formula. Hopefully that's straightforward enough for you. Again, this was for a finite geometric sequence. But what if we wanted to sum up an infinite number of numbers? Well, we're going to follow that same approach. This time we're going to go infinity. We're going to pretend for a second that we could actually plug infinity into our formula. So we have our starting value, right? If you plug in 1, 1 minus 1 is 0, this all drops, your initial value is 3. Okay? So I'm going to have 3 times 1 minus. This is going to be my r value, because we're looking at something that's written in this form. Hopefully you see that. Yes? So my r value is going to be 2, and I'm going to raise that to the infinity power, because I'm looking for summing up an infinite number, over 1 minus 2. Well, 2 to the infinity power is going to be some massively large number, in which case there is no solution. There's no finite sum that can come out of summing an infinite amount of numbers in this sequence. Okay? This sequence is 3, 6, 12, 24, etc. You're just going to get bigger and bigger and bigger and bigger and keep adding things. So there is no solution. If you want to get fancy, we would say that this diverges. Those of you that have read Divergent, okay? It does its own thing, just like in Divergent. It does its own thing, goes its own way. In this case, it's going to infinity in some approach. All right, but what about this one? So this, again, we're looking at a sub x r to the n minus x. So s sub infinity is going to be equal to 4, 1 minus 1 half to the infinity, over 1 minus 1 half. Well, 1 half to the infinity, that's like saying 1 over 2 to the infinity, because 1 to the infinity is just 1. 2 to the infinity is some really, really, really large number. If you take one cake and divide it amongst a lot of people, you get really close to this number being 0. Well, 1 minus 0 is 1, times 4 is 4, over 1 minus 1 half. 1 minus 1 half is a half. 4 divided by a half is equal to 8. If you take this geometric series, okay, you add all those numbers, it's going to converge, okay, or close in upon the number 8. Now, a good way to think about this is something called the painter's paradox. So, if I have one wall that I need to paint, and I paint half of it every day, and then I leave, okay, so I'm going to start and I'm going to paint half of this wall. That's about half. And then I'm going to go home for the night. When I come back, I'm going to paint half of what's left. And then when I come back the next day, I'm going to paint half of what's left, and then half of what's left, and then half, and then half, and then half, and then half. So how long is it going to take me to finish painting the wall? Well, you could argue that paintbrushes and thickness and blah, 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 but if we're really talking about half of the remaining space, it's going to take me an infinite number of days to paint one wall. So I'm adding up an infinite number of days, an infinite number of things, but it converges to the number 1. I'm getting close to painting one wall. So if I add up all of these numbers in this sequence, okay, I'm going to get really close to the number 8. And in fact, I will get to 8, because you're constantly adding things that are so tiny that really you're at 8. It converges. So, the sum of an infinite geometric series, we got to figure out when can we and when can't we sum to infinity. The infinite geometric series depends on what your ratio is. So we say if the absolute value of r is less than 1, which means if negative 1 is less than r is less than 1, then our sum is equal to this. A sub 1 is still your starting value. Okay, r is still your common ratio. And we can sum. Well, if you look back at this one, our common ratio was 2. 2 to the infinity caused a problem. Here, our common ratio was 1 half. 1 half to the infinity got us to 0. It converges. So likewise, if your r is ever between negative 1 and 1, your infinite series will converge. Okay? So r cannot be equal to 0. If r was equal to 0, we wouldn't have a geometric series to begin with. Okay? Let's use it. Find the sum of the following sequence. So first thing, we want to determine if this is geometric. So let's do our dividing. 9/4 divided by 3. Do the same thing as multiplying by a third. So 3/4. Test to make sure. 27/16 divided by 9/4. That's going to go to 1 and 4. That's going to go to 3 and 1, 3/4. So I have a common ratio of 3/4. Is 3/4 between -1 and 1? Yes. So this is going to converge. Let's go ahead and find it then. So our sum is going to be our starting value over 1 minus our ratio, which is 3/4. 1 minus 3/4 is 1/4. 3 divided by 1/4, same change, flip. S is going to be equal to 12. Okay, all because that R value was between -1 and 1. Okay, given this right here, which can also be viewed in this sense, all right, so let's find our common ratio. 3/25 divided by 1/25, 3. 9/25 divided by 3/25 is 3. Okay, so yes, this is geometric, and our ratio is 3. Okay, so our ratio is 3. Sorry, I had to cut the video there for a second. Is 3... Okay, first of all, our ratio is 3, and we're trying to sum up an infinite number. So if we want to look for a finite or an infinite summation, we have to ask ourselves, is our ratio between -1 and 1? Well, hopefully you told yourself that r equals 3 is not a number between -1 and 1, in which case this has no solution. We cannot sum an infinite geometric sequence if the ratio is 3. It's going to go to infinity, it's going to diverge, if you want to use that fancy word, okay? But there is no solution. So now, another way that you could have noticed that without looking at the sequence itself is looking at this right here. We know that this is 3 to the n, so that's some sort of geometric, because geometric implies exponential growth, okay? We've talked about that. Dividing by 25 is the same thing as multiplying by 1/25. So really, this is what we're looking for. We know then that our initial value is 1/25, and our common ratio is 3. So just from looking at this, because 3 is to the nth power, we know that this is going to diverge. There is no solution. You cannot find the infinite series. Okay, so just to clarify again, if r is between -1 and 1, then you can sum an infinite. But if r is not between -1 and 1, you cannot, and it is called a diverging summation. But you don't need to worry about that word until calculus a little bit later. All right, that should be the end of Unit 11. You've got a lot of stuff to review in your packet and a lot of questions for understanding. Take time to do the practice and ask questions if you have it. Have them. Yeah. Okay, bye.